In this section of chapter 3, we will discuss about balancing and then different reaction type and percent composition calculation. Chemical equations are concise representations of chemical reactions. And basically this is based on math of conservation of mass. That means you cannot destroy any element nor create a new element in a chemical reaction. So that's why balancing is needed, which makes sure that total number of elements of one particular kind that you have on the reactant side would be the same number on the product side. So now I'll go over problem number 11, chapter 3, and page 106. This is 11F. This is the balancing of a reaction. FeOH3 plus H2SO4 giving Fe2SO4 plus H2O. Okay, now we need to balance it. I ignored the state of matter, which are given in parentheses. By state of matter means it could be solid, liquid, or gas. So make sure you first double check whether we copied everything right, and then we'll start balancing. Now balancing of these kind of reactions can be done in more than one way, but I think it'll be faster if we pay attention to certain groups, like in this case SO4 So there are 3 SO4 groups, and I have only one SO4 on the left hand side, so let's multiply that by 3. Okay, so that gives me 3 SO4 on each side. And now if I look at Fe, I have 2 Fe on the right side and only 1 Fe on the left side. So in order to make it 2, multiply by 2. Now let's count all these different elements and different groups that I already have. So 6 oxygen, 6 hydrogen. Make sure you know that 2 times 3, that makes 6. And in parentheses we have OH. That means each of those elements will be multiplied by 3. And 2 Fe, we already checked that, 2 Fe. So 2 Fe checks out. Sulfate also checks out, 3 and 3, so I'm going to ignore those. So other than those, I would have 6 oxygen, 6 hydrogen coming from this compound, and then you would have a 6 hydrogen coming from H2SO4 in addition to sulfate, which I already balanced. And on the right hand side we took care of 2 Fe and 3 SO4. Now I have 2 hydrogen and 1 oxygen. So 2 hydrogen and 1 oxygen. On the left hand side I have 6 oxygen and 12 hydrogen. So that gives me 6 oxygen, 12 hydrogen. So on the right hand side, in order to get 6 oxygen and 12 hydrogen, I need to multiply that by 6. And now I can double check, and this has been balanced. So that means I have same number of iron on each side, same number of oxygen, same number of hydrogen. So it's a balanced reaction. In this slide, you're looking at a reaction between methane, which is a natural gas, and oxygen, giving carbon dioxide and water. Now, in parentheses, G stands for gas, so gas. And keep in mind, L, whenever there is L, you should understand that that's liquid, and S it represents solid. So these are states of reactants and products written in parentheses to the right of each compound. So this is another reaction where you see that this has been balanced. Now, types of reactions. There are several different types of reactions. One of them is combination reaction. In combination reaction, two or more substances react to form one product or one product type. So Mg and O2 gives MgO. So that's the combination reaction. Nitrogen plus hydrogen gives NH3. So in each case, you get only one product, but you have more than one reactant. And that's combination reaction. The second type of reaction is called decomposition reaction. Basically, you have a compound, you break it down into more than one. Calcium carbonate solid, when you heat, it breaks down into calcium oxide and carbon dioxide. Potassium chlorate, when you heat that compound, it breaks down into potassium chloride and oxygen. Similarly, NaN3, that breaks down into sodium and nitrogen. So basically, in decomposition reaction, one substance breaks down into two or more substances. Combustion reaction, as the name says, is nothing but reaction with oxygen. So methane reacts with oxygen, giving carbon dioxide and water. Propane, that also gives carbon dioxide and water, but quantities are different. So all these hydrocarbons, when it reacts with oxygen, would give carbon dioxide and water. And these are all combustion reactions because these are reactions with oxygen. Single displacement reaction. Sodium reacting with water gives you sodium hydroxide and hydrogen. Let me show you how this reaction happens. HOH, that's H2O. So basically, sodium goes with OH and H gets separated and two of those H's become H2. So this is how you can predict the product of a single displacement reaction. But keep something in mind, in order for this reaction to happen, sodium has to be more active than hydrogen. Otherwise, it cannot take the place of hydrogen. It's basically what sodium is doing. It replaced hydrogen. It pushed out hydrogen and then took the place of hydrogen. And that can only happen when a particular element is more active. So in this case, sodium is more active than hydrogen. I have included a table and you'd be able to look at that. The book also has the same table. Double displacement reaction. Silver nitrate plus HCl gives silver chloride and HNO3. This is a double displacement reaction. And let me show you how this happens. Split that into metallic and non-metallic part, or positive and negative part. Silver is +1, NO3 is -1. How do I know that? NO3 comes from HNO3, nitric acid. When I get rid of hydrogen, and I get NO3 minus, because each time you knock off one hydrogen, you develop a -1. Now, HCl, hydrogen is +1, Cl is -1. Now in a double displacement reaction, basically silver takes the place of hydrogen and hydrogen takes the place of silver. So this is how it's going to happen, and silver and Cl become silver chloride, H and NO3 forms HNO3. Now keep something in mind when you write down the formula. In this case, it just happened +1 and -1, but let me write down that. Silver is +1, Cl is -1, and that's why you have AgCl. If I had a metal with a different charge, then obviously it's not going to be 1 and 1 product. So you have to be careful when you write down the products of these reactions, single or double displacement reactions. Formula weight. Once we have a formula, it's pretty easy to get formula weight. You just look at periodic table. If you're looking at calcium, for example, look for element calcium, and underneath the element, you'd see its mass given. If I have 1 calcium, this 1 times that net mass. In case of Cl, I have 2Cl in this compound, so 2 times the value that I get in periodic table. And then finally you add them up. That gives you formula weight for this compound. Now, percent composition. We are calculating percent composition of carbon and hydrogen in C2H6, is ethane. When you're calculating percent carbon, first you must have mass of carbon on the top. This is mass of carbon. Again, by looking at periodic table, under carbon, I get that number. I have 2 carbon, and that's why I need to multiply by 2. And the bottom number is the total mass. Total mass, and that includes 2 carbon plus 6 hydrogen. So keep that in mind. That's how I got the top number is 24.022 and bottom number is 30.070 times 100. And that gives me 79.887%. So that's the percent carbon in C2H6. If I want to know percent hydrogen in this compound, it will be fairly easy, the same way. Now we'll have to have hydrogen on the top. 6 times mass of hydrogen. So let's maybe just put down mass of hydrogen. So you should have mass of hydrogen. I'm just putting down hydrogen. Make sure you get the number from periodic table and you multiply that by 6. This is the mass. Divide by total mass. Total mass is same as before, times 100. Okay, so whenever you're getting percent hydrogen, then total mass of hydrogen would be on the top, and the bottom would be grand total. Grand total means that includes carbon and hydrogen both. So I think the term used total mass is going to be a little bit confusing. The top number would be, I meant total hydrogen mass, and the bottom is total mass of carbon and hydrogen. Here we are showing you percent composition calculation for hydrogen and oxygen in H2O. So percent hydrogen will be given by 2 times the mass of hydrogen divided by the total mass of hydrogen and oxygen in H2O times 100. So that gives you about 11%. Percent oxygen would be given by mass of oxygen on the top, total mass on the bottom times 100. So 16, if I round off, I get 16 for oxygen, then 18.02 is the total mass of H2O times 100. So that gives me 89%. These two percentages, when added together, should give you 100 because these are the only 2 elements present in H2O.